Hello everyone. This is my presentation about a project called SmartBI. It's essentially a chatbot for discussing and visualize the data. And this presentation is intended to showcase a high-level design of the project to Professor Leong Sun. My leader is Moruta, and here's agenda. We have three sections. The first one, I'm going to take a look at the overlook into the project, which is the system architecture and the technologies used in the projects. The second one is the underlying technology, the underlying data structure. And the third one, I'm going to focus on the potential consideration for the project. Let's take a look at the system architecture. I decided to divide it into three sections, three components. The project is essentially a chatbot. Then we can never ignore the fact that we need to have a rack system and a large language model to support it. The job of the rack system is to extract chunks and embed text from the uploaded document from the user. And it then stores the embedding in a vector database for fast similarity search. The queries from the user are also embedded and matched to relevant document chunks, and the large language model uses retrieved context to generate accurate response. Some of the typical model is we can say like OpenAI or Llama. The project is intended to deploy it in a web app platform. It cannot just stay as a rack system. So we need a framework to build a web app, which is Django. It's a Python framework to build server side. Uh, so what is Django? Django is connects Django can connect users and the rack system and superset. For the superset is a open source tools to visualize the data from the uploaded document of the user. And Django can also manage user authentication, document handling, and chat history. Um, Django uses REST APIs and Celery for smooth asynchronous processing, and it offers a clean UI for uploads, chat, um, and visualization triggers. Django also prepares and sends structured data to Superset for instant visualize. About the data storage, um, the application database is going to be PostgreSQL. This is a direct database for the Django itself. The job of Postgres is to store users and documents and chat history. For the rack system, we have to have a vector database. It could be a Qdron or Pinecone. It's an available online solution. Um, the job of the vector database is to stores the text embedding for retrieval. About the file storage, uh, it could be a cloud-based solution or a local one, and it is to stores the uploaded raw document from the client, and the structured data from superset is stored in an accessible database tables. This is also being handled in the server layer in the server component, which is Django. About the underlying data structure, in the image you can see this is a data ingestion pipeline for the rack system. So everything starts from the raw data sources from the client. We have some tool like OCR or PDF extraction or web crawlers to pre-process the raw data after being processed will be chunked and then embedded and put into a vector database. For the RAG generation, um, the user start by making a query to the system. The query is also embedded and then feed into the vector database. And now you can notice the vector database have two things: the chunking data from the uploaded file, uploaded document from the client, and the user query. So both of these will be passed into a large language model and then getting the response back to the server. Um, to, ma to manage upload document, the system separates storage. Raw documents are stored in a dedicated system. It could be a cloud storage. Document metadata is managed in an application database, and processed document content, which is chunked and embedding, is stored in a vector database to support the RAG system. We have important considerations is that we have to include maintaining data synchronization across the storage system, defining a clear process for data extraction to support superset visualization, because superset also have a standard way to extract the data from a third party. In this case, we are third party. We are using the superset service. Uh, and we have to optimize the system for scalability and cost efficiency. The next one is the vector database. As you can see in the image, um, there's a few sources which the data came from. It could be from the user query, it could be from a text document, it could be from a web pages. And a model for embeddings would then transfer this into a vector embeddings and then put into the vector database. The job of the vector database is to store the document chunks as vector embeddings, which are numerical representation of their semantic meaning. These embeddings are indexed using techniques like HNSW or IVF flat to animal efficient similarity searches. To retrieve relevant information, the user query is also embedded and the database finds the nearest neighbor vectors. Mostly it is similar chunks. This process allows the RAG system to quickly identify contextually relevant information within the documents. Last but not least, we are going to talk about the structured data for visualization. It is a very important component in this project. And also, we are going to talk about the chat history and the user data. So a critical component of SmartBI is the structuring of extracted information for visualization in superset. This involves transforming unstructured or semi-structured data from documents into a tabular format that superset can readily utilize. The large language model plays a key role in this process, identifying and extracting relevant entities, relationships, and data points based on user query or predefined schemas. For example, we envision creating entity tables to represent key elements within documents, relationship tables to capture connections between these entities, and query specific table to present data directly relevant to a user's visualization requests. This structured data prepared by SmartBI forms the foundation for generating meaningful visualization in superset. And this is also handled in the Django framework. As you can understand, it's a server because As I said, superset expect a standard of data format, and we cannot just put a raw or even a vectorized data to supersets. We have to define it in a standard way, structuring the data. So we push it to a superset before getting the response back, which is a visualization uh, of the data. And about the chat history and user data, beyond document content, Smart BI will also need to store chat history to maintain context within user conversations. This data, along with user-specific information such as uploaded documents and preferences, will be managed within our chosen database infrastructure. This ensures persistent and personalized user experience, allowing user to revisit past interaction and their associated documents. Chat history is very important because the project from the beginning is intended to for clients who are some of the very important people in an organization. So any discussion or visualization data in any conversation needs to be stored so they can revisit next time they want. This is what they don't want to lost forever. So we need to store this conversation somewhere. But the last session I want to dedicate to potential features for the project because simply discussing and having getting the visualization from superset back to our project is not enough because realistically speaking, um, it is a very ambitious project because people they put their very important document to our service and they they don't just want to discuss or getting the visualization. We have to have a feature that enable multiple people, many people to collaborate with each other. And at least it could be a chat between users or a collaboration between users. And by doing so, we need to have a core service. And I'm going to introduce one of them, which is a real-time presence awareness between users. You can understand it as the online and offline status. It seems very simple, but it's the core foundation for any collaborative features if you want to implement in the future. First, I want to talk about one definition of this system design, which is a heartbeat. So you can understand the heartbeat simply as um, the client periodically send a signal to the server so the server can be aware that this client is currently being online or not. Here is the definition of the heartbeat. The heartbeat signal should be connectionless and lightweight for improved performance. So we're using the UDP as a natural fit for the sending the heartbeat. It is a low value time interval between consecutive heartbeats will result in an increased system load and poor performance. But in the contrary, a high value time interval between consecutive heartbeats will introduce a delay in detecting the start of a client. So therefore, the interval delay should be finely tuned for efficiency and accuracy. And how we're gonna finely tune this is depends on um, our use case when we bring it into production. Um, this image shows how should a heartbeat look like, and it's just simply as a user ID as a key and a timestamp indicating in which point in time they are online is a value of the key. So here's a high-level design for the present platform. We are going to divide it into two separate services, which is a present service and a real-time platform. And the definitions of the real-time platform is a published subscribe service for streaming the client's present status to the subscriber over the persistent SSE connection. But if we are using Django, it has an extension which is Django channels, and it is natively support WebSocket connection, and it's it could be considered as to be better than SSE connection. So since we choose Django to be the server-side framework, then WebSocket connection will be the chosen one for the high-level design. So the present platform should track the following events to identify any change in the status of the client. Here is the flow. The subscriber first will when the first time when they come online, they will have a HTTP connection to the present service to get, let's say, a list of friends status, and the present service will have its own present database, and this is could be a Redis database because Redis in this case serve very well for our purpose. And but the clients in general, we do not connect to the present service directly. We need to have another component, and we call it real-time platform. This platform is dedicated solely for um, the publish and the subscribe mechanism between clients and the subscribers subscribe to to a publisher through this platform, and this platform will um, if we want to have any information about the status of any client, we have to go through the real-time platform, and then from here the real-time platform will publish uh, will sending heartbeats to the present service, and then the service would publish an according corresponding event to the real-time platform. And after having the information from the present service, the real-time platform will use this information to manipulate between the subscriber and publisher. So how does the present platform identify whether a user is online or not? In this image, you can see everything starts from the server receiving a heartbeat from a client, and we are going to have a logic to ask if an unexpired entry of the user exists or not. If it doesn't exist, we publish an online event for the user on the real-time platform. And if it does exist, we only update the last heartbeat timestamp in the present store. Um, for the case that it doesn't exist, we further add an entry for the user with an expiry limit in the present platform. So to put it in order, this is how it works from start to finish. The publisher, or we can just call the client, create an, let's say, WebSocket connection with the real-time platform. The real-time platform sends a heartbeat signal to the present service over UDP. The present service queries the present database to check whether an unexpired record for the publisher exists in the database. The present service infers that the publisher just changed its status to online if there is no database record or if the previous record has expired. The present platform publishes an online event to the real-time platform over the HTTP put method. The real-time platform broadcasts the change in the present status to subscribers over the WebSocket connection. And the present service subsequently insert a record in the present database with an expiry value slightly greater than the timestamp for the successive heartbeats. And the present service only update the last active timestamp of the publisher in the presence database when an unexpired record already exists in the presence database because there was no change in the status of the publisher. What about detecting if a user is offline? So it's functioning the same way. Everything starts from the server receiving the heartbeats from the client, or you can just say the present service receiving a heartbeat from the real-time platform. And we are going to introduce another definition, which is a delay trigger. And simply put, the delay trigger is just a timer concept to check after a period of time if there is no the server receiving no heartbeats, then the server can decide if the client is offline and online. So if let's say the delay trigger is set to 1 minute, and after 1 minute, the server does not receive any heartbeats from the client, then we can decide them as offline. So here's the flow. The delay trigger queries the present database to check whether the database record of the publisher has expired. The present service publishes an offline event to the real-time platform over the HTTP when the database record has expired. And the real-time platform broadcasts the change in status along with the last active timestamp to the subscriber over the WebSocket. So when it comes to the presence service, there are going to be a lot more problem. Let's say, what about uh, people using our service on a mobile phone? And when it comes to a mobile phones, um, the problem about jittery connection, which is they can come online, offline very often, and it's becoming very random. It's one of the biggest issues when we are talking about the present service. But here I'm just introducing a high-level design which represent a core concept for any future collaborative uh, functioning in our service, in our projects. And this is the last part of the presentation. Thank you for thank you everybody for listening. Again, the presentation is intended to showcase a high-level system design for Smart BI. The development process needs to be carefully discussed between people in the team. Thank you very much.